My name is Samir Khan and I work for Maplesoft as a product manager. I spend a lot of my time talking to users, engineers, scientists, mathematicians, and I try to help them better understand and use our tools, technologies, and services. I then take their feedback and put it in the product development process and then keep development on track so we develop tools to meet their needs. In this event, we'll present 4 civil engineering calculations and talk about their implementation in math software. And along the way, I'll ask you to think about the context and importance of math in your work. So I'm going to start by asking a question. What differentiates an engineered product from a crafted product? Well, you might be a civil engineer, a mechanical engineer, or a chemical engineer, but the answer is always the same. The difference between an engineered product and a crafted product are calculations based upon mathematics, science, and physics. Now, I do have a grudging respect for engineers who did calculations before the advent of cheap computers and modern software. One of my personal engineering icons was a Victorian engineer called Isambard Kingdom Brunel. He lived and worked in the UK in the 1800s. He designed bridges, steamships, and railway stations with nothing but his own intellect, diagrams he drew himself, and calculations he did by hand in his paper notebooks. His original calculation notebooks are still preserved at the University of Bristol, and if you spend time perusing and reading his calculation notebooks, it's clear that his understanding, his analysis of forces and stresses were based upon a deep understanding of structural behavior. And that was whether he was designing the Great Western Steamship or the elegant arches on the roof at Paddington train station in London. This is an example of the Clifton Suspension Bridge in the UK. It was based upon an original design by Brunel and opened in about 1860. And on the right is a photo of a page of one of his calculation notebooks for the same. So when he needed to work out the parameters in the suspension bridge, perhaps the length of the chain or the height of the connecting rods, he derived the appropriate equations, and that involved some calculus. He substituted in numerical values and approximated the results. He used whatever tools were available at that time to do his number crunching, his math, but his paper notebooks were the center of his technical desktop. That's where he did his calculations, wrote down his notes, and drew his diagrams. And in many ways, paper is still the most intuitive working environment of all. I work in a tech-heavy industry, software development, and in the middle of meetings where people are talking about code and development, people still take notes on paper. It's because there's a certain immediacy, a certain tactile feedback that you get from paper that's hard to reproduce elsewhere. You need more than paper for engineering calculations. You need computational support. But the development and the evolution of technology and software in particular has dramatically increased engineering productivity. Now, here's a somewhat coarse timeline of the evolution of mathematical computing for engineers. In reality, the picture isn't as simple or as clean as this, but this serves our purpose for the story I want to tell. I'm going to pick an arbitrary starting point, the 1800s, mostly because 2 gentlemen, Charles Babbage and Isambard Brunel, were contemporaries and lived and worked at the same time. The story actually starts with Babbage's analytical engine in the 1800s. Although Babbage never built a full version in his lifetime, the analytical engine contains many of the concepts fundamental to computing today, such as loops, branching, and memory. Now, between the 1800s and the 1950s, mathematicians and engineers developed analog computers, and these worked on mechanical and electrical principles. And the first general purpose automatic digital computer was built by IBM in 1944, and that actually used punch paper for people to write and enter programs. The use of computers to solve engineering problems didn't really get started until we reached an inflection point in the 1950s, and that was when IBM developed Fortran. That's a high-level programming language that replaced the somewhat more low-level ways of writing code. And Fortran is still a popular tool for numeric computing, and it's still being used to some extent today. The growth of programming languages in the 1970s, like C, essentially democratized software development and let many more people with different skill sets like engineering develop targeted application-specific software. And that's when we saw the first FEA tools like Nastran and the development of numerical libraries such as LinPack and the NUG routines. And now we just need one more ingredient for something very special to happen. And that happened in the early 80s, where we saw the introduction of relatively cheap microcomputers. And that oxygen-rich environment ignited a Cambrian explosion in the diversity of software for engineers. That was the decade that saw the adoption of spreadsheets, early computer algebra tools like Maple, and numerical tools like MATLAB. And cheaper computers also saw a dramatic increase in the number of application-specific, domain-specific tools to solve very, very targeted problems. And that brings us to the present era, where the world of Babbage and Brunel actually collide with modern engineering calculation software. So as the lucky beneficiaries of software evolution, one of the pleasures of being an engineer today is actually the vast amount of software that we have at our disposal. My laptop currently has CAD packages, math tools, physical modeling tools, and programming languages, and all of these are simply a double click away. And that's reservoir of engineering expertise, those resources, it would have been astounding even just a generation ago and beyond the frame of reference of earlier generations. Now, at the current time, for developers of calculation software like MapleSoft, the math is already a solved problem. All the math routines that civil engineers need for 99% of the work are already there. They're robust, they're quick, but the challenge for us is how do we address the broader engineering requirements that don't necessarily revolve around the math, that of documentation, auditability, usability, and not least pleasure. Calculation tools should be a pleasure to use. They should have simple game mechanics, but the flexibility to do many different things. I said earlier that a piece of paper is still the most intuitive problem-solving environment. There's a certain tactile feedback that you get from paper that you don't get from a spreadsheet or a programming language. Well, with MapleFlow, we've tried to reproduce the design metaphor of paper, but with computational support for math. So let's put that to one side and talk about civil engineering calculations. Now, some calculations are already formalized in design guides, such as Eurocodes or the International Building Code, and the equations in those design guides tend to be mathematically simple. They're nothing more than our basic arithmetic operations, but there are lots of them, and you need engineering experience to determine how they're implemented. Some calculations actually need more mathematical insight. You might need to do some matrix math, solve an equation, and you might need more computing horsepower as well. In all cases, civil and structural engineers need reliable software. They need validated software to help them. Some actually use application-specific software that's appropriate for a limited number of scenarios. And those are the domain and application-specific tools that I mentioned earlier in the previous slide. And these are absolutely fine if you're happy to work within that restricted framework or if you're good with a black box. If you actually want to enter your own calculations and do your own math, then you have two major choices. Some people use Excel. Excel is free at the point of access, but it does come with a longer term cost that's measured in terms of risk and maintainability. And some use engineering calculation and programming tools. They offer greater flexibility. You can implement your own equations, analyses, and designs, but they do need more technical knowledge and mathematical experience to use. And there are many fine commercial calculation tools on the market, and one of those is MapleFlow. There are also some free tools. They all have their own unique and compelling design principles. Those design principles are choices the developer has taken that might tilt the scales one way or another. So what calculations are we going to look at in this webinar? We've chosen 4 applications. Each application is chosen to illustrate a specific concept or a group of concepts. We'll start by looking at a design calculation, the torsional and lateral loading of a steel beam. The core concept in that application is documentation, auditability, and units. We'll then look at bulk group coefficients. That'll illustrate how we can put away lookup table for bulk group coefficients and easily implement the math. That'll demonstrate numeric equation solving. Number crunching or iterating over numerical data can be time consuming, and that'll be illustrated with a slope stability calculation. And we'll finish with spatially varied flow. In that application, we'll need to numerically solve differential equations. After each calculation, I'll actually stop for a beat. I'll pause and pose a question for people to think about. But let's start with this. So, an engineering calculation isn't just a calculation. They're not just the sum total of all their arithmetic operations. They have properties, context, and requirements beyond the basic number crunching. So an engineering equation does exist in a physical context. They're actually derived from physical laws, and that means they're inherently dimensional. The lengths, forces, stresses, moments, pressures all have units, and the units are important, and you need to get them right first time. And as a part of the broader requirements, you need to document and communicate your design calculations and make sure all your assumptions are recorded. You'll need to ensure that there are no mistakes. You might even need to generate a report to deliver to a client. I refer to all of that as calculation management. You could do the calculations in Excel, but spreadsheets are difficult to follow and debug. You could use a word processing tool to write your documentation, but that does mean that your math and documentation live in 2 separate, largely disconnected worlds. For example, the load on beams in steel frame structures usually acts through the shear center, and that means that torsional effects can be safely ignored, but that isn't always the case. A torque may actually arise from an eccentric load that results in torsion and hence a twist angle. The torsion may be significant enough to control the overall design, and engineers need to know and recognize when torsion dictates the design and apply the appropriate engineering rules. A lot rides on applications like this. They're safety critical, so you need to make sure your equations and results are correct. And that could mean ensuring that there are no typos in the equation and ensuring all the unit conversions are correctly applied. So this is a video of what the calculation could look like if you were to do that in MapleFlow. So what have we got? We have text and images. There are parameter definitions with units. Those flow through to the results. The equations are readable. Any changes automatically cascade down the length of the worksheet and all the parameters update. And then you can export the document to a PDF. This is what the calculation would look like in a spreadsheet. Excel's great with data-oriented work where you're dealing with rows and columns of numbers. It's great for reconciling your expenses at the end of the month, but for equation-based work for engineering, you have to ensure readability and ease of auditing. Also, your unit conversions have to be correct, and Excel doesn't really address those broader engineering needs. So before I go on to the next application, here's a question for everyone. How do you manage the risk associated with calculations? Do you actually throw caution to the wind, or do you treat calculations with a modicum of deference and respect? So managing calculation risk is really no different to managing risk elsewhere in your life or in your work, especially if your living revolves around calculations and the IP in those calculations. Let's move on to the next calculation. When you're designing bulk groups, you need to calculate the bulk group coefficient. That's the ratio of the factored force or the available strength of the bulk group and the shear capacity of a single bolt. Once the coefficient is known, a bulk group can be designed for any load. Bulk group coefficients are actually tabulated in the AASHTO Steel Construction Manual. These tables are generated from a theoretical approach called the instantaneous center of rotation method. More on that later, but it involves lots of math, lots of equations. The bulk coefficient tables are actually limited to common bolt patterns and a set of predefined load eccentricities and angles. If you want non-tabulated values, you need to extract them with linear interpolation. That's clunky and human intensive, and anytime you get people involved, you add risk. So here's some background on the instantaneous center of rotation method. It involves several assumptions, but ultimately you end up with 3 simultaneous equations in 3 unknowns. And the equations are here. They're implicit. That means they have to be solved numerically. To solve them, you need a numeric iterator. You might be familiar with the goal seek or the solver tool in Excel. It's another window, another interface that sits on top of the spreadsheet. You basically have to set up the spreadsheet to minimize a value by varying other values subject to certain constraints. And in this case, you'd set the sum of the forces in the X and Y direction on the bulk group to 0 by varying the instantaneous center of rotation. And if you want to automate the solution, you need to write VBA. So we've got the spreadsheet, you've got the solver tool, and you've got the VBA, and you have to make them work together. You might try to make your life easier by using name ranges, and that's going to help a little. So here's what the implementation could potentially look like in MapleFlow. To do the number crunching, you're using a numeric equation solver, the numeric results of units. Those fall through from the user-specified bulk positions, which also have units. And the whole calculation could be linked into a broader analysis and automated. So here's another question for everyone. How do you share calculations? How do you actually manage that whole process of transferring the skills of one engineer to another? Let's say an engineer leaves or retires, were the knowledge and skills of the ex-employee captured in a form which can help someone new hit the ground running? So on to the third calculation. Let's talk about slope stability. So a slope is simply an inclined boundary of soil, perhaps with highways or buildings at the top, and you have to make sure that the slope is stable. Otherwise, buildings might fall down, and to ensure the stability of anything on top of that slope and to minimize the risk to human life, you need to determine the factor of safety. That's the ratio of the maximum stress soil can sustain to the actual applied stress. There are several methods for quantifying the factor of safety. I've implemented two in Excel and MapleFlow, the ordinary method of slices and Bishop's method of slices. The first, the ordinary method of slices, is actually a conservative approach to estimating the factor of safety, but it's the basis, it's the foundation of more sophisticated techniques. And they're based on the assumption that the plane of failure is a circular arc. If the failure circle cuts through the bottom of the slope, that's known as toe circle failure. You're looking at the MapleFlow implementation of the ordinary method of slices on screen. If you've been watching carefully, you might see a parameter being changed from a value in meters to a value in feet, simply by associating the unit with a number. You'll also see some of the equations that you need to implement the ordinary method of slices. There's a lot of number crunching involved. For efficient computation, you have to successfully fill arrays or vectors with intermediate values, and the final calculation of the factor of safety actually involves iterated additions. So you need to do a decent amount of number crunching. This is what the corresponding worksheet would look like in Excel. You have to deal with unit conversions yourself. And of course, the equations are much more difficult to decipher and ensure that they're correct. They're in line and in programming notation. Before we go to the next calculation, here's another question. Can you determine the return on investment of new calculation tools? Can you put a number on how long it'll take for the potential increase in calculation efficiency to pay for the investment in new software? Generally, engineers are expensive to employ, but tools are cheap. For the sake of argument, the overall cost of employing an engineer might be $100 an hour. If you can make that employee conservatively 3% more efficient with a tool that costs $1,000, well, that'll only take maybe 2 months to pay back the cost of the tool. And that's only counting the direct increase in the efficiency of the engineer. In addition, there are broader, less easily quantifiable increases in efficiency across the whole organization. We could be more detailed in our calculation. You can include things like taxes, holiday time, IT support, discount rates, but often an order of magnitude determination of ROI is enough. On to the final calculation. Let's talk about spatially varied flow. That's open channel flow where the flow rate varies with longitudinal distance. And there are many examples. The eaves troughs that you probably have attached to your house are examples of open channel flow. The surface profile is described by a differential equation given here. For a subcritical flow, downstream conditions, such as freefall, actually determine the water surface profile. And the water depth reaches the critical height, that is the minimum energy height near the freefall. That's the boundary condition on the differential equation. This is what the solution looks like in MapleFlow. You have natural readable mathematics notation. We've used symbolic math to derive the differential equation, and then a numerical solver to solve it. That numerical solver is just a command that you type in. And there's a plot of the surface profile as well. So what would this look like in Excel? Well, I simply wouldn't do this kind of problem in Excel. Excel doesn't really have any built-in tools for solving differential equations numerically. You have to code a routine yourself, perhaps using an Euler or a Wundercutter method. But then you have to worry about step sizes, error handling, and so on. A complicating factor is that this is a boundary value problem. So you have to pick an initial value, see if the boundary condition is met. If not, you go back and choose another initial value. You can automate some part of this process in Excel Solver tool, but it's still clunky and kludgy to do. Now, before I end the presentation, here's one final question. Do you actually enjoy doing calculations? I think for the right type of person, and that includes me, calculations are actually a pleasure. I'm that kind of guy, and I'm not apologetic about it. Everything from getting the equations down to hunting down errors, making sure the results are correct. It's pleasurable. I think it's a bit like the accomplishment a writer gets from authoring a beautiful piece of prose or a kid gets from making Lego. The common factor seems to be simple game mechanics and immediate feedback. All you're doing is brushing paint on a canvas, tapping keys on a keyboard, or clicking Lego blocks together. But with those simple game mechanics, you really do have unlimited creativity and you see your results straight away. So that brings me to the end of this presentation. I want to make a few points just to wrap things up. Throughout this webinar, we've been demonstrating civil engineering calculations in MapleFlow. Flow is a tool that we've designed to imitate the design metaphor of paper, but with a math engine under the hood. Your equations are readable. You can use units. You can write down the assumptions and the context of your work with everything displayed in front of you. That reduces the risk of calculation errors. The nature of the environment means that you can easily extend and tailor your calculations to cover other cases. And we've also built in a degree of tactile feedback, a degree of immediacy to the tool, so you feel connected to your work. The interface runs quite away in the background, and it automates the things that you don't want to do while you get on with the more important stuff. And that makes MapleFlow a pleasure to use. If you'd like to know more, then I'd encourage you to pop over to our website. The address is right there. There's a gallery of civil engineering applications for steel, concrete, timber, hydrology, geotechnical analysis, and many other disciplines. You can also get an evaluation license of the software.